Hello, good morning, good afternoon, good evening. Thank you for joining us today. This is Keao Caindec with Mocana, and thanks for joining our webinar today on securing containers in industrial IoT gateways and endpoints with TPM 2.0. So if you're joining this, it means that you have probably worked with or are thinking about working with TPM technology. So today I have with me Dean Weber, our CTO, to help us navigate through understanding what TPM is, why you might want to use it, and how to actually use it. So let me get started. First, I'll introduce Dean. Dean, welcome, Dean.
Thank you.
Dean is the Chief Technology Officer of Mocana, and previously he was the CTO at CSC Global Cybersecurity, and previous to that was CTO at Applied Identity, which was acquired by Citrix. There's a theme here, hold on. He was also Chief Security Architect at Teros, which was also acquired by Citrix. And throughout his career, he's been involved deeply in security across both public and private sector, and also spent several years in the U.S. Navy working in physical and electronic security. You'll find Dean when not at an airport or on an airplane, at events and speaking with at both industry events or industry associations and helping our customers. So welcome, Dean.
Thank you for having me.
All right. And then I'll just introduce myself. My name is Bill Gates. Well, actually, it's not Bill Gates. But the point is that we are now living in a world where identity theft is more common, and where having a business card or a name tag that says what your name is not much different than the way systems communicate or rely on each other. You're not really sure, even though a computer might say that I am this computer. There's no way to really authenticate, or not no way, but there are very limited ways of being assured that the identity of a device that's communicating with another server or another device is the device you think it is. So today what we're going to cover is really the aspects of how you enable strong authentication assurance and how you use TPMs to really improve the trustworthiness of devices. You're all familiar with Alice and Bob, right? Taught in the security world how certificate authority works and how Alice can share a secret with Bob to either establish a secure encrypted tunnel or to provide a shared secret that they can both use to share information. I know the basic way that it works is Bob would send something to a certificate authority, and the certificate authority would sign it and say, thanks, Bob. Okay, if you say you're you, here's a way that I'm going to provide that back, and here's what you can share with others who want to validate your identity. So when Alice wants to communicate with Bob, Bob sends over that signed certificate to Alice. Alice asks the CA if that's really Bob. The CA says, yep, that's him. And then Alice says, oh, okay, well, I can trust you, Bob. Here is a one-time password or some shared secret that we can both use. And it's encrypted in a way that only Bob can unlock with his private key. Now, the great thing about this is it's a well understood application of authentication technology and PKI that we all depend on today when your browser hits a server or when systems authenticate with each other. The problem is that you still don't really know whether Bob is really Bob, because that CA is still trusting that Bob is saying that he's Bob. And if it's a system or two computers, how does that system, that embedded system, actually establish the trustworthiness of its identity, which has to kick off this whole process? So, Dean, maybe we could talk a little bit about kind of the authentication today and what you see as some of the challenges.
Sure. So, I mean, as the slide represents, there's no shortage of challenges associated with identity and identity proofing. Roots of trust in the context that we're talking about them today is secure identity validation, one of the steps in 863 that we'll talk about a little further on, as well as a secure storage facility to include the ability to create new associations as needed with a hardware random number generator, et cetera, et cetera. So there's a lot of concept around the TPM in terms of how we can use TPMs to help solve some of these problems. And once we've solved the root of trust problems, then we can rely on the root of trust for chains of trust that get you over things like man in the middle and self-signed certs. SCEP and OCSP, those are historical certificate management utilities, both of which are not very friendly to industrial environments, which is primarily what we're talking about here today, because of the fact that the SCEP enclave actually has to be associated with or in direct connection with the device that it's provisioning, and OCSP is all about how do we manage that certificate's life cycle once it's been deployed. And of course, in an industrial world, once you've deployed the device, it can be in a land far away. So bringing SCEP and OCSP to the device is sometimes problematic. And then, of course, we don't have an attestation model that works effectively with just certificates, and what that leads to is weak authentication.
Great. So, I know some of the companies that we work with use SCEP today to enroll a device or to deploy a digital certificate on a device, and it's fairly manual. How does that impact scaling or handling its security? You mentioned that it's tougher to do in an industrial environment. Why is it problematic?
Well, typically the SCEP and OCSP-based enrollment where certificates are used in the industrial communities is those certificates are provisioned at manufacturing time. So there's a couple of problems. One is change of ownership, right? How do I take that certificate that was issued by manufacturer A and it is now in the possession of operator B? There's not a good way to transfer ownership or to attest to ownership, which brings in all kinds of questions about supply chain and the efficacy of the platforms themselves and the components that went together. So SCEP is just a problematic approach to a distributed environment. I mean, if everything was securely networked and everything had, assured roots of trust associated with it, SCEP might still be worthwhile for us. But the answer to the question is they're not, right? And probably the biggest offender of that's the United States government with SHA-1.
Mm-hmm. Mm-hmm. You mentioned attestation. Tell me about attestation. What is it? What's attestation? Remote attestation? Why is it important?
Attestation is about validating that you are who you say you are, and that can be done in a local format where using a simple Bob and Alice model where Bob holds up his driver's license and Alice is able to validate the information on the driver's license compared to the person that's standing in front of you. And if you've gotten a driver's license anytime recently since July 1st, or if you've gone on and gone ahead and signed up for the new driver's license, you'll find that there's a lot more identity proofing that is going into the creation of the identity of a driver's license so that it can be relied on more heavily for more security-oriented purposes like getting on airplanes and crossing the Canadian or Mexican borders. So attestation as a local attestation is absolutely critical in validating that the identity or the element of identity that is being presented is indeed what they say it is. So it's not spoofed, it's not stolen, it's not already used someplace else, et cetera, et cetera. And then we bring in the concept of remote attestation, which is the ability to do that over a network, over the wire or over the air or halfway around the world. It doesn't matter. But how do we create an attestation model by which we can validate that the presented identity is indeed the element that we expect to see when it authenticates?
Okay. And when you talk about authentication, right, there is the notion of a root of trust. I'd love for you to talk a little bit about that and the different levels that NIST uses to determine the assurance level for authentication. So you can go from everything from here's a self-signed cert to leveraging a root of trust, hardware or software based. Can you talk a little bit about what a root of trust is and also about these authentication assurance levels?
Sure. So in concept, the root of trust is exactly what it sounds like. It's where trust starts. And there are lots of different models of trust out there in the world today. Hardware like a TPM, firmware/hardware like a TE Trust Zone or like a PUF, and then software, which is just an embedded certificate. That may be in a file system or maybe in a protected file system with limited access to authorized entities within the file system. The root of trust is the basis for trust that you build upon. And by building on it, that means that, okay, so I've got an identity associated with the root, and I want to add a second element of identity to that, where I say, here is a measurement of a BIOS that I want to add to the chain of trust established by the root. And by doing that, you endorse the root certificate to the BIOS certificate, and you have a net new cryptographic value that represents the trustworthiness, the cryptographic trustworthiness of those two elements. So how all that fits into authentication is that once those chains are established, the elements that go into making up those chains have to be verified. So the authentication assurance that is 863 latest guidance is all about how do we validate that those elements of identity that have been given to and provisioned to a device or an entity or a subsystem, that they are indeed who they say they are, that they follow the appropriate path, and that we can rely upon them, that the assurance level that we can rely on them is valid. And 63 points out 3 different levels, one which is basically username and password, not very secure. 2, which is a multi-factor authentication where you must have at least 2 different forms of identity being provisioned, and that might be the root key of the platform and the certificate provisioned from the owner-operator or from the manufacturer's facility combined and endorsed together, where they can together be validated that it is the platform based on the root of trust and it is the identified device based on the provisioned certificate. And then if you go all the way up into level 3 has to have that based solely in hardware. Basically, you have to have something that is recognized as a immutable root of trust. Now that's a word that gets bandied about a lot, immutable. In today's day and age, there is nothing that is guaranteed. What we mean by immutable root of trust is that it's sufficiently hardened to the point where it is going to take a significant period of dedicated time by an individual or group of individuals to be able to uncover the secrets that root contains. So when we talk about hard cryptographic authentication, we're talking about just that. We're talking about a TPM's private key, because the way the TPM is constructed is there is a unique element that is a private key that is associated with that bit of silicon that is immutable. As long as the silicon itself is intact, you will have that guaranteed root. And then additional certificates are associated with that as they are developed or deployed, and we endorse those into the process. We also have the concept of specialized keys, which we'll get into here in a minute, for certain elements of transaction like transport or storage or platform or attestation or signing keys, et cetera, et cetera. So all of these key sets, all of these PKI and certificate functions all come together as a function of authentication assurance under NIST 863.
I mean, it seems like everything is so fundamentally tied to being able to trust the identity of the platform, right? So when think about if you're encrypting communications with SSL or IPsec, or encrypting the storage on a device, or validating that the boot or the applications or the OS are all as they should be. All of those measurements and communications are in some way using the identity to validate that that's true. And I think what I'm hearing is that oftentimes it may have authentication built in, but it may not be built to the high standards. And I think what we want to talk about today is how TPM can help with this and how it can help to achieve very high levels of authentication assurance in a system, and how then it can be used to protect many of the other cryptographic functions associated with protecting storage, containers, communications, etc. So let's jump into TPM. First of all, you sit on the Trusted Computing Group, TCG's group there. Tell us about what TPM is.
Well, TPM is just what it sounds like, right? It's a trusted platform module. It is an electronic silicon component microcontroller that is put into a system that is electrically connected to functions on that board. Again, what the TPM provides is that non-repudiation of the original element of identity, because it is literally cast in silicon and protected by a group of algorithms by the various TPM manufacturers. The TCG spec, currently 2.0, provides for a number of interface functions that you can use the TPM for, like give me a random number, or like associate a new key pair with this particular function or this particular software, or attest to this new value. And before we can attest to it, we have to enroll that certificate, and then we have to create a trust chain associated with that certificate through endorsement. So all of these functions can be based on the storage, the random number generator, and the ability to create new content in terms of cryptographic elements based on the TPM architecture. And there's any number of different operating commands that you can use to and from the TPM. That's part of what the good news, bad news is about TPM, is that the good news is you can do all those things. The bad news is that the interfaces are still somewhat hard to use in general purpose computing.
Right. And how broadly deployed are TPMs today? Well, where are we seeing TPMs?
Well, so if you haven't looked, pretty much every client and server-based platform on the planet has a TPM in it. Whether or not it's being used is a different story. But TPMs have been being embedded in IT systems for, over a decade now. Many people use them for different functions. Some use them for explicit functions. I think it was 2013 when Microsoft came out and said we're going to throw everything at the TPM. We're going to use the TPM as Microsoft's root of trust on a platform. And if you want to hardware qualify or hologram the Microsoft operating system on platform, that operating system had to have access to the TPM and had to be able to read and write functions from the TPM in order to establish the root of trust hierarchy for that particular Microsoft operating system. And if you didn't have that, you were not, quote unquote, hardware qualified or able to hologram the operating system. Overall, the TPM architecture is pretty straightforward, and one of the reasons why we're seeing a significant interest and uptake in the industrial community is because identity and identity attestation, as well as authorization, is a significant problem in the industrial world. These are networks that were not traditionally designed to be open to accessed. But as they have grown and as they have morphed away from proprietary communications protocols into more internet-like or network-like protocols, problems have continued to arise since those platforms were never designed with security in mind. So as next generation platforms are being designed, there's a lot of interest in the industrial communities about building TPM architectures into those, or TPM-like architectures. Again, TPM is not the only form of root of trust. However, it is what I believe is the strongest root of trust available on commercial markets today. So the TPM architecture is pretty straightforward, actually. And as I said, it's not that the architecture is difficult to understand. It's just difficult to use because of the vagaries of the interface commands. But again, so the primary concepts here are endorsement, secure I/O, the protected execution environments like a TE trust zone, sealed storage where we can seal certain elements, or complete storage subsystems using specialized key sets developed from the TPM. We can use the TPM query and nonce specifications to do local and remote attestation, and this provides for the ability to validate trusted third party by inclusion of their certificates either at manufacture or at enrollment in the overall transactions associated with an identified device.
Super. I know we've been working with some of our partners at Mocana to actually put this into practice, into usage. So can you talk a little bit about what we've been working on with Avnet and Xilinx and Infineon with regard to TPM?
Certainly. So this board was a developmental board that the four of us came together to work on the concept of being able to develop the board to a ISO IEC 62443 3-3 level 3 or level 4 validation. And ISO 62443, for those that don't know, it is an industrial specification similar to NIST 853, but very focused on the industrial community and the elements and artifacts necessary to be considered and generated on a platform in order to achieve those compliance requirements. So this particular board was designed specifically to address the needs of a 62443 3-3 level 4 environment, where the Xilinx UltraScale Plus has two internal mechanisms based on internal crypto that is tied to an internal PUF, a physically unclonable function within the FPGA itself, and then that is then extended to BIOS and first stage bootloader transactions. And the second stage of that then is we added a TPM pre-processor so that we had a platform root of trust, not just a processor root of trust, and that we then used the platform root of trust to basically validate that the processor root of trust has functioned properly, and then when control is turned back over to the platform, that we can take the second stage bootloader and beyond and create those trust chains using X509 trust chaining that is necessary to get to that top level cryptographic value that is the cryptographic value that represents the cryptographic trustworthiness of the platform and how you convey that to validated requesters. So there's a lot involved here in terms of software elements, and firmware elements, and hardware elements. There's a lot of good use cases that can come out of this for the industrial communities. And ultimately, this board was designed, as I said, as a development board. I think it has 9 programmable interfaces on it, so you could have 3 WAN and 2 LAN and 2 WiMAX or whatever type interfaces. But you can do a lot with the board, and it's an excellent architecture for TPM integration.
And it supports time-sensitive networking, TSN. It's a high-performance board. It's as a development platform or as a production system that you would embed into some sort of product you're building. It's a great example. So hardware's there. Of course, the applications then need to be able to use the TPM and integrate with the other cryptographic elements and CPU on the board. So now let's talk about how you actually do that. How do you take a system that you're building, either with a TPM chip built into it or using a TPM PMOD interfaced into that printed circuit board? How do you actually end up using it? So, Dean, talk to us about what's involved for developers to figure out how to do that.
Remember when TCG started this effort, they started it as an engineering effort. There were a lot of engineers involved, and because of the vagaries of creating a trust platform, there was a lot of documentation that went into this. The original TPM spec was over 1,000 pages, and the most recent TPM spec is over 2,000 pages. So there's a lot of documentation available on where and when and how to use the chip. However, as I mentioned earlier, that's both a boon and a bane. The bane being is that, you know, your engineer is going to have to sit down and read a couple thousand pages of TPM specification just to figure out how to use it in operational constructs. And then there's ways that we can help with streamlining that by using published APIs and abstraction platforms between the TPM and the various elements that are using the TPM via published APIs.
Okay. So let's talk a bit about how Mocana is actually helping companies and what we have as the base platform. I'll start a bit and then hand it off to you, Dean. At a high level, right, we have our software, Mocana Trust Point. It's an endpoint, IoT endpoint security software. It sits on an embedded system. It supports a very comprehensive set of cyber security controls, from having a FIPS validated crypto engine to having being able to secure the and verify the boot process, to being able to secure ensure confidentiality by securing the various transport mechanisms like TLS or SSL, IPsec, SSH. So if you're building a device that needs to either communicate over SSL or IPsec, or you're implementing SFTP over SSH, or even supporting multicast or just general Wi-Fi, we have our software that can be integrated with your application to handle all of these functions. Now, one of these is our trust abstraction layer, and that abstracts the underlying operating environment, which is fundamental to how we simplify integrating with TPM. Dean, can you talk about that trust abstraction layer and what it does and what, yeah.
Sure. I mean, the simplest case is the one we already mentioned, the differences. And the idea is that the interface specifications changed extensively between those two, where you really didn't want to necessarily have to rewrite your hardware calls in order to take advantage of the new capabilities. Specifically around the concept of those interface changes, we created an abstraction layer. And initially we created it for ourselves because we make a lot of TPM calls and a lot of TPM function resolutions on our own to do what we do. And then we make that available to any other authorized callers on the platform as well. So if you needed to make a direct hardware call through our abstraction platform, we publish the APIs to let you do that. And the good news about that is that you don't have to continue to change any calls that you are making, whether it's through us or using our technology directly to the TPM. The abstraction platform handles all of that interpretation between the standard API calls and all of the underlying functions, of which are, I think there's close to 200 on TPM 2.0 now.
Right. I mean, that's a big value to developers and device designers. So being able to take thousands of pages of TPM documentation, boil it down to a simple set of APIs that you can use and carry out, implement what you need to from a security perspective, all leveraging TPM certified keys based on a very strong, trusted root of trust. And I know some of our customers have been able to get up and running in and testing all of their use cases for using a TPM in as little as several days up to several weeks, which cuts down their time from months or years to get this up and running. So, and that's the important part. That's the important part, right? We know that devices are not secure today that are out there. and they should be. The problem is, it is oftentimes very difficult for the device designers and product security engineers. So what we're trying to do is make it easy enough so we can start to build very strong security into everything from industrial devices and avionics controllers all the way down into consumer devices. In a simple way, right, we'll typically provide source code or binaries that you can use, compile into your application, C++, Java, or even Python, and that compiled image can exist as a binary or as a set of libraries, but then that gets loaded in to the actual target device. Mocana can support devices with as little as 64 kilobytes of RAM on up to much larger systems. Some of what we do can fit in as little as less than 20 kilobytes. So it's designed for highly constrained systems. When we talk about TPM, you're probably not talking about a system that is that constrained. So we have a couple of questions here. One is, Dean, how is TPM different than T?
Well, TE is an ARM construct based on a firmware-based immutable trust zone. And the primary difference between TPM and TE trust zone is that the TE trust zone is electrically alterable. It's an on-processor construct, where the TPM is an independent silicon function that is independent of the processor and therefore not susceptible to the types of electrical alteration that the processor functions are. So in terms of the strength of root of trust, TE trust zone is a good concept. As more things come out of the ARM PSA architectures and the M23 and M33 type models, I think we'll see a lot more people migrating in that direction. But if you really want a hardware root of trust, then you have to go to hardware, not electrically alterable processors. And that's where TPM comes in. And in many cases, including the one that we just talked about, where we use a TPM for base root of trust, we add in other trusted functions, could be a TE trust zone, could be a PUF, could be other forms of trust architectures which are then tied back to the hardware root of trust that is a TPM.
Yep.
Hopefully that.
So we started out this presentation. Thank you. Yeah, we started out this presentation talking about authentication and being able to trust that Bob is actually Bob, and how while we have PKI and basic authentication methodologies, you need to be able to trust that that endpoint device is actually that endpoint device, and that TPM plays a very strong role in that. So talk about how now, if you have TPM on a device, how you handle identity proofing while you're through digital authentication.
Well, there's a lot involved there, probably more than we can get into on this presentation. But the short answer is that the association of a external certificate trust platform, whether that's a CA or a HSM or a MIM architecture, where we are going to associate that immutable identity that is on the TPM with additional external certificate functions through an exchange of values, and that those exchange values can be cryptographically proven to be exactly what they are saying that they are, what they purport to be, and then using that as the form of digital authentication at the level of identity proofing that 863 level 3 calls for.
Mm-hmm. And you mentioned MIM. We have a question from the audience also on, can you elaborate on that and how this might work with a device that also has a SIM?
So a SIM is another
or alternatively a SIM, yeah.
Yeah, exactly. SIM is another form of potential trust anchor that is being heavily considered in the industrial spaces. We've got a number of our partners that are actively working with SIM technologies, where a TPM is either not appropriate due to size constraints or power constraints or price or whatever that is, where a SIM does provide a level of identity that's not immutable, but it is transferable via the architecture of the SIM, particularly the nano SIM and eSIM type architectures, and it does come with a certain amount of associated trustworthiness between how you provision the SIM, how you use the SIM's capabilities as a firmware-based root of trust, with software components that would then be associated with that firmware root of trust, i.e. certificate chaining. So the SIM technologies are certainly going to be up and comers in the industrial space. I think we'll see a lot more interest in particularly low power devices where they don't have the power budget to support a full-blown TPM, and those SIM technologies can then be used as a suitable alternative.
Great, thank you. So obviously securing keys and storage is a big primary use case for TPMs, has been in the server and laptop space. And that's being able to use the TPM keys. Securing transport, talk a little bit about that and using TPM to secure transport and why that's important.
Well, it's not just TPM, it's the entire trust stack, right? So again, what we have is a trustworthy platform based on a root of trust, which is using an endorsement process going to give you a top-level value of wherever you decide to end the trust chain. That could be at the top of the OS, that could be at the top of a specific application function or executable, or it could be the entire platform. But one way or the other, you're going to have a cryptographic value, a hash, if you will, that is the cryptographic representation of all of the components together that make up that system. And using cryptography to do that, that is relatively immutable based on the strength of root of trust. If you then include those values in the trust exchange that goes on for transport between two trustworthy elements, and you use that as the basis for allow or deny for the connection to continue to the point where data can actually be transferred bidirectionally across that connection, you now have a mechanism by which you can say only trustworthy devices can be talking to or be utilized by another trustworthy device, which kind of takes a whole slew of the detect and respond type technologies out of the picture.
Right. Yeah, exactly. So many of the approaches to security today, detection, monitoring, firewalls, are put in place fundamentally because you can't trust the device or the communications. And this gets to the heart of solving that problem, which is a very significant one and important for systems like this. We talked about remote attestation and being able to now tie that TPM to the CA as you would have done through enrollment, and being able to verify remotely that system. Let's jump ahead to containers and SSL a little bit more in detail. For some of you that are more technical, this is going to get a bit deeper in what we're doing and how we do this for containers in particular. The backdrop is, if you are running, typically these industrial devices of all kinds or IoT devices have been connected to some sort of control network. Now those same devices are being connected to an industrial IoT cloud. Sometimes they're the same device, and you have problems where you have different surfaces of attack of a device that's connected to both the internet as well as to a control network. Solving that problem can be done by, or securing that can be done with TPM and also by implementing containers to separate applications, which is important. I'm going to jump ahead to that. So let's talk about a couple of use cases here of how we secure this with both with remote mode of operations for Docker containers.
Sure. So again, the design here, because there's a fundamental problem in both virtualization and containerization where the interpretation that occurs between the shell of the container or the VM and the actual hypervisor underlayment of the platform, which is the shared services. Because there is no way to bypass that interpretation, as is the nature of virtualization or containerization, you cannot directly tie a workload to a specific TPM function. Therefore, you cannot directly attest to the efficacy of the workload from the hardware TPM. So barring getting the manufacturers to fix that, which I've been trying to do for the better part of 15 years, What we can do is we can attest to the values internal to the container or the VM using a remote attestation model, whereby measurements during DevOps or DevSecOps of the container or virtualized engine itself, or the virtualized machine itself, can be measured and be based on some remote root of trust in the remote model, or could even be based on a secondary root of trust, which could be a software TPM or a firmware-based TPM associated with the development of those functions, and then extended to those functions and validated through what is known as TPM remote attestation, which is a query and nonce structure by which you can ask the infrastructure for what is its value. The nonce is returned at that value. That value can be a known expected value based on an out-of-band mechanism that you can then validate between the two entities. And you can actually do that both ways. So you can, over time, work to a full bidirectional trust model between containerization, virtualization, and the underlying hardware platforms, shared platforms that they're running on.
Right. So NanoTap is our abstraction layer. So there would be a NanoTap library on the remote side within the Docker container. We'd establish a secure connection to the NanoTap library that can talk to the TPM locally, and we have a server between there. But effectively, we are able to now take either TLS sessions and Docker containers and enable those to use the TPM and do it in a secure way. So if you're building an IIoT gateway or a PLC or some other industrial device or an IoT device that has a container, it could be a Docker container, an LXC, a VM. We would approach it in a similar way where we can leverage the TPM and enable a higher level of security and measurement of those containers to ensure they haven't been compromised. So bridging into a couple of questions here that we have. One of them was on how can TPM module protect data from being copied, dumped, or injected within the device? How can TPM save data from RAM, buffer, et cetera, buffer overloads?
Well, we could have a much longer conversation about that particular element, but the short answer there is that if only trustworthy connections are made between trustworthy devices, there would be no platform for that injection to occur. Now, that being said, we're all vulnerable at the stern. That's an old nautical term from an old sailor. But the short answer there is that, with physical access, all bets are off for most platforms today, whether it's differential power analysis or logic probes assigned to memory or processor function. At the end of the day, the ability to operate on clear text data while it's being processed to and from RAM is problematic. We can assure that only the platforms that are communicating with it over a network are trustworthy devices. However, with physical access, that is not possible. That being said, there is work being done by various memory manufacturers and others to solve for some of the problems associated with flash and RAM, where they will have their own, kind of like the Xilinx UltraScale Plus PUF and 2 cryptographic functions for BIOS and boot, where there will be specific functions in those memory arrays and storage arrays that can then validate the I/O function in and out of memory at processor, inject via DMA, et cetera, et cetera.
So before I forget, we hope you'll also join us on August 15th for another webinar on protecting IoT endpoint devices and communications. And we'll focus on the dangers of relying on threat detection. We see a lot of over-reliance on that. And finally, we've got one more question here. Many SOCs come with OTP, which are not electronically reprogrammable. Can such processors be considered a TPM?
So again, the TCG answer to that is no, not unless they meet the TCG requirements, which means they have a hardware-based immutable root of trust. If we're talking about a one-time password, the password is not a hardware-based root of trust. So the short answer there is no. What the system-on-chip vendors are doing is they are creating other forms, like we mentioned with Xilinx and the PUF, where there are other functions that can be assigned a value, a root value that can be considered similar to TPM, not as strong as TPM. So you'll never get to 62443 3-3 level 4 as an example with a puff or a TE trussel. You have to have a TPM.
Great. Well, thanks very much, Dean. We would love to continue the conversation, but we're out of time. If you do have other questions, be sure to contact us. You can go to our website at www.mocana.com. You can also reach us on our Contact Us page, and we would love to talk to you and help you to implement TPM or discuss any other questions that you might have about securing the supply chain and securing your systems. So with that, thank you very much, Dean. Thanks for your time today.
Thank you.
And
thank you all for listening.
Those of you, thank you very much for joining us.
Take care.
Bye-bye. Have a great day.